Okay, just about the time to start recording. So we are moving on to the consideration for multi-span high contrast elastic beams. So basically, if we look at the similar scenario as we did for rods, but for elastic beams, well, certainly it's now very different from physical perspective, because the displacement is supposed to be perpendicular to the direction of the beam now. So these are the equation of motion, fourth order, just as we started talking yesterday. And now, instead of the rigid body motion in the form of just translation, we have a possibility of translation and a possibility of rotation. So that complicates this scenario. And because of that, I was mentioning yesterday that it becomes really difficult to classify the types of boundary conditions for which the global low frequency regime will become possible. So we ended up just looking at some popular types of boundary conditions. So namely the case of the free ends. So when there were no moments and no shear force here at the ends, that was one option. And another would be simply supported, so precluding displacements and moments. So that would be another popular type of a boundary condition. Okay, so now introducing this scaling where we have local coordinates. So now local coordinates vary between these two values. So the length is always 1. And then these lambdas, which are again related to scale frequencies, they are related to each other. So actually we could express all of them through 1. And the important assumption to make here is that we should, because we have already a small parameter in the form of ratio of Young's moduli, we also need to make some assumption about the ratio of densities and the ratio of lengths. So we are assuming that the ratio of lengths are all of order 1. And we are assuming also that the ratio of densities is of the same order as the ratio of Young's moduli. So these are the assumptions, and starting from that, we can expand the displacements and these quantities lambdas, and we're expanding them as lambda to the 4th. And then at leading order, we get this thing, so we have just the 4th order derivative equal to 0, subject to this boundary condition for each of the stiff components. And the solution is then found nicely as the first order polynomial, which is exactly the rigid body motion of the stiff beam components. So the second part there, BI, is associated with translation, and the first part, AI, XI, corresponds to rotation. Okay, so now moving on to the problem for the soft component. So we can have the same 4th order derivative equal to 0, and we have these continuity conditions here. And so now we already know the values of displacement of the stiff components appearing on the right hand side from the previous analysis of stiff components. Therefore we can find it. So it's just, I mean, I'm not showing the procedure how to find it here, but it's certainly possible to find it. And as a result, we have a usual cubic polynomial with some constants, and these constants are certainly all defined, expressed in terms of the components of the rigid body motions, right? So if we wanted to arrange them in a matrix relation, we could do it something like that. So basically, our approach is to express all of these coefficients related to soft components through the ones which were related to stiff ones, which were associated with rigid body motions. And now, knowing all that, we can already consider the next order problem for the stiff components. So now you can see the inertia term here, well, appearing here. But we already know UI 0 for all of them. And certainly we can solve this 4th order equation then. But actually we don't even need to solve it, because all we need is the solvability condition of the next order for these stiff components. And so if we substitute them, all we know into this equation, then what do we need to do? Well, basically, we just need to integrate over the domain of this stiff component, right? So, for example, if we take the first equation and just start integrating, so if we compare, this is the equation of the fourth order, so lambda to the power 4 times ui naught. And so for the stiff component, remember this ui naught was just the first order polynomial. So it was ai xi I plus bi. So therefore, not surprisingly, this is what we get here, right? So we have this, but this is not sufficient because this is only giving us, roughly speaking, the number of the number of equations coinciding here with the number of stiff components. So we need one more because we have two more. We have double number of coefficients. So at next step, what usually people are doing, so we add a multiple here, so that is giving us some sort of a distance relation to a moment, really. So we are multiplying it by xi I and also integrating all of that. And that gives us exactly 2n1 plus 2 equations for the constants ai and bi, which were the stiff, the elements of the rigid body motions of stiff components. And so now, once we've got 2n1 plus 2 equations for 2n1 plus 2 constants, then obviously the associated determinant will be equal to 0, and that will give us a polynomial equation related to frequency, and that would indeed be the frequency equation. So in case of a beam, the procedure is slightly more complicated compared to the rod. So what we can observe is that first note to make is that certainly we have twice more equations compared to the rod. That's one thing. And second thing is that, well, certainly the simply supported ends could be treated similarly, but we will not present the details here, so it could be found in the paper that I was referring to. Okay, so now let us just show a few examples how this might work for beams with some finite number of components. So for 3 components, certainly it's relatively straightforward. Well, some people could still try and do it by hands, but still, you know, it's quite an exercise. So the approach that we have gives us the system straight away, because we know that we have 2 stiff components here. So each of these 2 stiff components does involve 2 constants associated with rigid body motion. So A1, B1, A3, and B3 here. So after we compute that and just write down the associated determinant, we end up with something like this. So that gives a clear 3 options for lambda to the power 4 for the spectral parameter. Another option is if we consider now a 3-component rod, but being simply supported. So something like that. So here for the free ends, we are precluding moments and forces at the end. And here we are precluding moments and displacements. So this cannot move anywhere. And so what we can see is that actually if we perform something similar, I'm not giving the system here, but the equation, well, there is a difference now. You can see it. So in the first case, when we were having this free ends, there was this root of 0, the eigenvalue of 0, which was corresponding to the rigid body motion. So that was a 0 eigenvalue for the rigid body motion of the beam. In case of the simply supported, certainly rigid body motions will not appear. And as a result, we don't have this root appearing in the frequency equation. Well, 3-component rod was certainly not a very difficult exercise. So let's try 5 components. So in this case, we may certainly expect, well, there are 3 three stiff components. So we will have 6 equations in the system, and indeed this is what we get. And then after writing down the associated determinant and factorizing, this is what we get here. Well, again, this example is still quite doable. Although if we were to try and consider a 5-component rod by hand, well, I guess in case of an eager student, it would probably keep them busy for at least a week, maybe more. So now just to give you some illustrations showing the comparison of these asymptotic results that we have with the exact results in numerical simulations, you can see that it does work reasonably well. The roots here, lambda to power 4, they just correspond to the non-zero roots of the previous example that we have considered for a 5-component rod. There were 2 quadratic equations for lambda to power 4, and basically these are the 4 roots that we corresponding to 4 different types of eigenmodes. So certainly these the reason why the approximation works reasonably well is because the contrast is chosen at a relatively small, so 0.01, it's a good value of contrast. So if we would take it as 0.1, certainly we would see the picture would be spoiled here. Okay, so a few remarks about beams now. So our colleagues have developed the approach to take on board the possibility of random vibrations in beams, so it has been extended further. A few more ideas how this could be developed. Certainly, this is only the global low frequency regime that I was illustrating for beams, but there is a possibility to consider local low frequency for this multi-span beam system. So this is probably a plan for somebody to do in the future. We could also consider incorporating the effect of elastic foundation for these beams, or for some parts of these beams. And certainly could study other types of boundary conditions, but here we looked at the 2 most typically occurring for beams, the free ends and the simply supported ones. Okay, so I guess that's enough about beams. And now let us try and develop this research in a slightly different direction. So we will be considering now still a scalar problem in elasticity, but a multidimensional one. So we'll be talking about anti-plane problems in elasticity. So to start maybe from the most, well, not the most, but to start from a quite general geometry here. So suppose we are talking about this kind of a 2-layered cylindrical body. This is a cross section presented here. So these boundaries, gamma naught, gamma 1, and gamma 2 are just, some simple curves, but pretty arbitrary. And also, so there is a hole in here, and we are interested in the anti-plane motion. So that would mean that there is just one displacement, which is perpendicular to the plane XY shown here, right? So in this case, well, if we denote U1 and U2, the displacements associated with these 2 components here, the standard Helmholtz equation is governing the motion. In case of time harmonic dependence, harmonic independence, yeah. And so C would be the shear wave speed. So mu is the shear modulus, and rho is mass volume density here. Okay, so immediately we would want to introduce the scaling, which would be similar to the one that we have seen previously for the rods. So we would want to have a ratio of shear moduli, which would be acting similarly to what we've had before for the ratio of Young's modulus. So it will be essentially the ratio of stiffness, and then we have a ratio of L, well, L is some kind of a typical size associated with the domains. So it could be, well, for this case, could be, say, some kind of a maximum of the width of that if we define it properly. Well, if these were circles, then it becomes very clear in terms of radius. But you know, there are many other, or we could think about some kind of normalization of the length of the boundary. So there are many ways to think about a typical length scale here. Then we have a ratio of mass densities, rho. We have scaled frequencies, again lambda I, and we have a scaled Cartesian coordinates. Okay, so that leads us to a formulation for this problem written in terms of the scaled variables. So just to point out that the delta here is a Laplacian in x, y, and delta there now it's a Laplacian in terms of the capital X and capital Y. Yeah. So in this case, we will have, as you can see, we have a softer component 1 and a stiffer component 2. Of course, another setup is also possible. It was considered in this paper, but today I'm talking only about this one. And so as we remember yesterday, when we were considering rods, we would have this low frequency effect when the soft component is subject to Dirichlet type of boundary conditions and the hard component has a prescribed Neumann type. So this is why we are considering it here. So we already know that. So we know that there'll be a Dirichlet condition on gamma naught, a Neumann condition on gamma 2 on the outer boundary. And on the interface, again, we have continuity between the displacement and the stresses. So it is already written like that here. And we have a natural small parameter, which will be the ratio of mu over L. And we would also assume that L is of order 1. So basically mu, the ratio of stiffness is again the main small parameter that we operate with. Okay, so now if we wanted to start with the global low frequency perturbation scheme, we would start with similar. Yeah.
Can you go just to the previous slide, please?
Sure.
So both mu and L are dimensionless.
Yes, they are both dimensionless. Yes, it's a ratio of shear moduli and ratio of some typical sizes. Yeah.
But you don't assume individually on them how big they are. They just have to be. You want one of them to be smaller than the other.
Yeah, we just want the ratio, but not necessarily each of them. Yeah.
So if L is finite, mu is small. If mu is finite, L is large.
Yes, but for the purpose of this talk, we are assuming that L is of order 1. So basically, it's just mu much less than 1 in this particular example. But of course, we could consider other. But I would say then it becomes a fully multi-parametric analysis, and it would be potentially interesting. Yeah.
Yeah, I'm just wondering whether you could not get away just with mu, that you don't really need epsilon. You could just say mu is already dimensionless, right?
I mean, just to say, well, yeah, that's possible. I think it's just a matter of, yeah.
Why
perhaps you're right, yeah.
If you already have a parameter, a dimensionless parameter.
Yeah. I think we could do that. We could just call mu a small parameter and then say L over the 1. Yeah, absolutely. And that would spare us a letter. Yeah, I think you're right. Yeah, thank you, Kira. Yeah, that's right. Okay, so basically, just happens that I cannot really change it here, but let's assume that, you know, all this mu and rho are of order epsilon, L is of order 1, and we operate in terms of epsilon in what follows. So this will be the expansions of displacements and spectral parameters. And then once again, following the same approach, we start with a leading order problem for a stiff component. And this is what it is. So the inertial effect vanishes at leading order. So you just have a Laplace equation subject to these two Neumann conditions. So therefore, the solution is very straightforward. So finally, here we don't really care about the boundary. The boundary, well, it's not arbitrary, but there is a wide class of boundaries that would satisfy it, but still you get a rigid body motion solution. And then when we start looking at the problem for the soft component, well, there are two Dirichlet type conditions here. And so this one is pretty clear because it was fixed there along the curve gamma naught. And in this case, well, C is some rigid body motion. So that makes a sort of a model problem. So really, we need to find a harmonic function, a plane harmonic function that would satisfy this property. It would be 0 on one boundary and 1 on another boundary. This is a kind of a, well, we can't really call it a fundamental solution, but it is a sort of a basic function in a way. So we are denoting this as H1 because, of course, it will depend on the nature of the curve. But we assume that this can be found in some certain examples. Certainly we can find them, and so therefore our solution for the soft component is like that. Okay, so now assume that this H1 is known, and we can proceed to the next order analysis for the stiff component, which would give us an equation like that with some more boundary conditions. Yeah, and so now all we need to do is consider the solvability of this problem. So we are integrating over this stiff domain. We integrate the equation of motion. And then for the left-hand side, we are employing the first green identity. And so we are reducing it to the boundary and looking at the boundary condition. This one, at the homogeneous one, it's clear that the first integral must vanish. And that gives you now something quite useful because, well, A2 is just the area of this domain D2, and that gives you an estimate for the eigenfrequency. Oh, sorry. Yeah, that's the one. So you can easily get a formula for lambda 2 squared for an arbitrary shape of gamma 1, well, within this certain class, of course. So let's consider an example how we can apply this. So suppose that we are having a square cylinder with a circular annular inclusion, and because, I mean, if that was two circles, then you could easily write down an analytical solution in closed form. But if you have a square and a circle, then the analytical solution becomes problematic, well, in closed form. But at the same time, within our approach, we can certainly find a straightforward asymptotic solution here. So starting from these equations of motion, and we have boundary conditions, so U1 should be 0, okay, from inside. Yeah, so that is fixed. The outer domain of the square is free. And we are again considering this anti-plane motion. And the two continuity relations are here. So the one for the displacement and for the stress. And here we have certain dimensionless quantities here. Yeah, so I'd say, yeah, epsilon really is mu here. Yeah, because L is order 1. Well, we could assume that we could take epsilon equal to mu in principle. Yeah. Okay, so now if we just start searching for this harmonic function, that would be so H1 of R1. So all we need to find is a harmonic function in this annulus that would be 0 on the interior part and would be 1 on the exterior part, on the gamma 1. and it's certainly doable to find a harmonic function which satisfies these two conditions. Here is the solution. Yeah, so it is in fact a logarithm. So logarithm will satisfy, you can certainly verify that it would satisfy both of these conditions here. And so once we found H1, then we can integrate, so use that formula for lambda 2, get the curvilinear integral done, and we can get the frequency. And certainly knowing all that, we can also have the eigenforms as well. These are, of course, approximate eigenforms, but what is interesting is that, well, say if that was two component rod, as we did yesterday, we would not be surprised if we had the eigenform having a constant for the stiff component, and we have the same here. But for the soft component, we used to have a straight line, and that was correspondent to the homogeneous deformation at leading order. Whereas here, we have a logarithmic curvature, so it's not a straight line, but it's close to it. And this is clearly the effect of curvature. Okay, so now let us generalize the approach to the case where we can have a multi-layered circular cylinder. So it could be, again, a finite number n of these layers here. And certainly, since we've done the approach for the rods, a similar thing could be done for cylinders. So now instead of the one-dimensional equation, we just have a two-dimensional equation governing the situation, and we operate in polar coordinates. But apart from that, the whole approach is very similar. So what we will have, so the equation of motion would be, well, in case of axisymmetric, is certainly like that. Then the boundary conditions for this particular one, since we have two soft components, the very inner one and the most outer one. So therefore, we would want to prescribe the Dirichlet conditions here, and the continuity would be, as usual, the continuity of displacements and stresses. So such type of a problem can be considered. I don't think we need to look into all of the details of that, because we can just summarize the approach, but the certain algebraic formulas may be found in the paper that I referred to. So basically, if we start the global low frequency perturbation, we will start it in the same fashion. So we will expand the displacements and the spectral parameters, and this lambda squared would be of order epsilon. That would provide the right scaling. And then once we consider stiffer components at leading order, we will find out that the solutions are rigid body motions. Then we will look into softer components, and we can find the solutions there in terms of logarithmic functions. And once we would substitute into this next order for stiff components and consider solvability, we will result in a polynomial equation for frequency. Okay, so just to give a few examples of this approach. So, for example, this one is a three-layered cylinder. What is important for us is certainly the number of stiff components. So luckily we have just one here. Therefore, the equation, the approximate equation for frequency would only be a quadratic one, a very straightforward one. Well, it's linear in terms of quadratic, really. So these coefficients here are expressed in terms of logarithms, and not surprisingly, the eigenform would have a constant associated with the rigid body motion of the inner part, and some logarithmic functions associated with deformations of softer components. So that is a three-layered. Now, if we look into five-layered, so we have two stiffer components, so we're likely to have a bi-quadratic equation. So we'll have two roots for that. And this is what the eigenform would be. So here you can see a lot of logarithms, but this parameter k is certainly important. In fact, k may be either positive or negative, which gives you two possibilities here and the two eigenforms. So again, the stiff components perform rigid body motion. This is why we have constants here. Okay, so I guess that is probably sufficient to illustrate this approach. And now let us consider an antiplane problem, well, shear motion again, but with a slightly different setup geometrically. So we would want to consider a three-layered laminate. So we will consider a symmetric version now in slightly more detail. And then I'm also hoping to present some results of asymmetric laminate also today, after we deal with the symmetric one. Okay, so in this case, we start from the governing equations, which are useful to be written in terms of the stresses. So to get the stresses involved here, so classic antiplane elasticity, the stress components are expressed through the derivatives of displacements, and this mu is against shear moduli. So we have two skin layers and one inner core layer, and the displacement is again out of phase displacement, so it is the one which is perpendicular to the plane shown here. One more thing is that this index Q is either C or S, corresponding to either core or skin layers respectively. So rho conventionally is the volume mass density. Right, so the boundary and continuity conditions that we impose here, for example, we would want to consider traction-free boundary. So this condition here on the skins, and the interfacial conditions, so continuity for displacement and normal stress here on the interface. Okay, so if we want to consider this problem, certainly we can derive the dispersion relation. I don't think we need to go through the details, so it's clear you're getting the traveling harmonic exponent, substitute them, find the associate dependence on the transverse coordinate, and then substitute into boundary and continuity conditions, and from solvability you get these dispersion relations. So what you can see is that it certainly does involve both a wave number and frequency. So small k and small omega are conventionally denoting the wave number and frequency in dimensional form, but we certainly want the dimensionless quantities. So kh, well, this is capital K dimensionless wave number, and capital omega, the dimensionless frequency. So we choose to dimensionalize within this within the core layer. Yeah. So as a result, we have two such quantities, alpha 1 and alpha 2, which appear inside. So this is a transcendental equation. And generally speaking, well, there'll be infinitely many branches here. But our idea is certainly to try and construct a polynomial approximation to it. Okay, so yeah, so h, mu, and rho, as usual, would be the ratios of appropriate quantities. So ratios of densities, shear moduli, and thicknesses here. Okay, so we may consider two scenarios which would be useful for us to see. We will see even more tomorrow, because tomorrow we'll be looking at vector problems of elasticity and the same approach realized there. In case of scalar problem of elasticity, it does make sense to look at two possible setups. So mu is our small parameter, and basically we want, as we will see later, for this global low frequency effect, which will be corresponding to this setup when the cutoff frequency will be small, we would want a double inequality to hold, a double strong inequality. So that would be mu much less than h and much less than rho to power -1. So these two types of scenarios definitely satisfy them. Well, they are still different because the main thing is in geometry. So in the first case, the ratio of thicknesses is of order 1, so we are speaking about roughly similar thickness of the layer, whereas in the second case, this thickness of the skin layer is much smaller compared to thickness of the core layer. So the second case is much closer to the classical sandwich type structure when you have a thin coating on top of this core layer. And the first one is something different. Well, actually, it is an approximation of the idea. The main idea here would be close to this photovoltaic panels. Yeah. Okay, so we will be looking at both of them. So this slide here is just to show the solutions, that the solutions can be found for displacements and stresses, but obviously they are nasty. They are not pleasant at all, just involving all these hyperbolic functions and so on. And all these, remember, all these alphas, they are also the square roots involving k and omega. So the structure of the exact solution is pretty unpleasant here. However, we certainly want to derive an efficient approximation. So if we start looking at the dispersion relation and set k to 0, so the wave number to 0, in this case, we will obtain a much nicer equation. And if you remember some of the things that we were talking about yesterday, this is a very clear reminder. So we have ton of something times another ton of something equals something that was small yesterday. So that's the same structure like we used to have for a rod, but now we have it in vector problem of elasticity, in the scalar problem of elasticity, in the antiplane problem. And so we are interested in having small solutions for frequency here, so for omega. And so the global low frequency regime here would assume that both of the arguments of tan are small, and that gives us this simple approximation for the cutoff frequency, and this could be small. And the condition for this to happen, well, something like this, or the other way around. Yeah, well, if you invert it, the one that I was speaking or telling you orally previously. Okay. So this condition would also coincide with the results of the brainstem problem that we'll be considering tomorrow. But the difference is that it does not support a fundamental mode. So in the graphs of the dispersion diagram that I'll be showing very shortly, we would not observe a fundamental mode. So this is a graph of a typical dispersion diagram when we have no contrast, roughly speaking. And the other one, so if we want to have a high contrast, then we have something like that. So you can clearly see that the first mode becomes isolated, and that this quantity here at 0.17, well, this is exactly the first cutoff frequency, and that becomes small. And this is a result of the fact that the contrast is also quite pronounced. So you have here mu as 0.014. So for this high contrast, we can see how the mode is moving here closer to 0. Of course, the exact 0 will not be a solution. Fundamental mode is not supported in this case. Okay, so now what we can do, we can expand the dispersion relation. Just as Taylor series, you can expand all these hyperbolic functions in the vicinity of omega small and k small. So it's a long wave low frequency approximation. And so this will be replaced by a polynomial. And these quantities, well, gammas, they are involving all of these ratios. So ratios of stiffnesses, thickness, and density somewhere. So all of them are mixed together here. And that is why it is important for us to choose a particular setup that we are operating in. Because generally speaking, the problem is still multi-parametric. So here you have all possibilities for mu H and rho. But if we specify a scenario like we did, for example, say in case A, when mu is small, H is of order 1 and rho is small, in this case, we can certainly pick up the leading order behavior for these coefficients, and we will decide which ones we need to keep and which ones we may neglect. And so for the first case, just reminding you here, what is the first case A? It can be shown that actually all of these 5 coefficients are of order 1, and therefore at leading order we have this type of behavior. So rho and mu are both small of the same order, so their ratio is something of order 1. And the shortened form of dispersion relation may be formulated, something like that, quite simple. And if we wanted to test it and match it versus the exact solution to see how this approximation will work, we will get something like this. So you can see clearly that the approximate curve shown by this dashed line works very well. And also, it is worth mentioning that it does work even quite outside of this global, so strictly speaking, it should be working for k small and omega small, but as a matter of fact, it does work in quite a wide vicinity. Okay, so now the second scenario for the sandwich type structure is quite different. And as we can see here, first of all, these coefficients here, gammas, well, not all of them are order 1. Second thing, when we start and derive approximations, there are some internal cancellations. So as a result of that, we really need to keep the second term here for gamma 4. And also, well, we have some more of these dimensional, well, order 1 quantities here. And also we would need to iterate around the cutoff frequency because there are also some cancellations associated with the cutoff frequency. So as a result, after we apply all these things, we get this near cutoff expansion, which is something like that. And with this case, we can see again, it is working well. Well, what is the difference? We can see the difference in gradient. Yes, so in the previous case, it was going much, much more inclined to horizontal. So the gradient was smaller in the previous case. In this case, the gradient is higher. And we will see how this will affect on the approximations in the future. That would be tomorrow. Yeah. Okay. So now, if we want to get approximations also for that exact solutions in terms of displacements and stresses. Remember, I was showing you this pretty nasty for expressions in terms of hyperbolic functions. So that could easily be done. So again, we will see a familiar picture when this stiff component is a constant for the displacement here. And for the core, for the soft core, it will be a linear variation. So that example for the rod is really illuminating. It is appearing in much more advanced formulation. Again, the same kind of picture. Yes. So when you have a stiff component, you have rigid body motion type behavior and something like almost homogeneous deformation for a softer component. Okay, now moving further, let us now present the asymptotic procedure, how we can derive the approximate equation of motion. So I will only be dealing with case A here. Case B is also treated in the paper that I cited by Ludmila and co-authors in 2020. So when we are doing this, following this asymptotic integration procedure, so basically we need to start with a clever scaling, that's something like that, and that allows us to reformulate these governing equations in this form. And then we are just expanding all the quantities as asymptotic series. So these quantities here with capital letters and also V, they are all assumed to be of the same asymptotic order. And that allows us to have a asymptotically consistent procedure here. So we just expand these quantities as asymptotic series and substituting that into the governing equations and these continuity and boundary conditions, we may formulate the leading order problem, something like that. So you see a lot of terms have cancelled, certainly because of that. And now we must solve that together with the continuity and boundary conditions. And this is already a doable problem. So what we can spot, well, the nice ways to start is this equation here. So for V naught S, so we can find the solution for a skin, so for the outer layers, to be independent of the transverse variable. So this is the first step, and this is like, you know, with dealing with when you try to open the sorry, I lost the word. Anyway, so that is really the cornerstone, I could say, because once we found that, we can also use it to express everything else. So all of the other quantities will be expressed one by one. So for example, knowing that, we can also look at the other displacements. So we have this condition here, and we also have that condition there, and also this is another ratio here. So combining this together, we will be able to find the condition, well, the solution for V naught C, which will turn out to be a linear function. And then using that, we can certainly find this S quantity, say 8S23C. Well, from here, you can see, for example, that if you know V naught S as so this function W, then you can certainly write down S13S and so on. So all of these quantities now will be expressed in terms of this function W. And this is what we will have. Yes, so they are all expressed in terms of this W. And this W, if we substitute it into, let me show you, into this equation here, that will actually provide the model equation for the, well, approximate equation of motion. Yes, there it is. So that would be the approximate equation of motion. And interestingly, if we were to rewrite it in original variables and then try to get the associated dispersion relation, we can rewrite it, and there will be a coincidence with the approximate, well, shortened dispersion relation that we have derived earlier. So there is certainly a direct correspondence through Fourier transform as well. So certainly there is a justification here that we can definitely see that this is exactly the correct approximate equation. Right. Now, just to say a few more words about the asymmetric laminate. So that is where we have, well, slightly more involved algebraically, I would say, but also the thing is that there will be a combination of two motions here. So there'll be a fundamental mode as well in this case. So it would not be possible to separate it into symmetric and antisymmetric. And so therefore, as we will see, the dispersion relation will turn out to be, you know, well, the approximate one will turn out to be a factor of 2. Right. So if we formulate the problem here, so it's quite a similar one, but now we have 3 layers. For simplicity, we also assuming that the material of the outer 2 layers is the same, so the same shear modulus and the same mass density, but different thickness. And standard continuity and boundary conditions. So, for example, we could, well, for the purpose of dispersion, we would not need the forces here. But if we wanted to derive the governing equation of motion, in this case, these forces will appear in the resulting model, and they do appear indeed in the paper itself. Right, and so we have the continuity condition here in terms of displacements and stresses. So when we derive the dispersion relation in absence of the load, of course, if F1 and F3 are both zeros, we will have something like that. So again, not very pleasant one involving these transcendental functions. And so alpha 1 and alpha 2 are these square roots here. So again, capital K and capital omega are the scaled wave number and frequency. And all these ratios here are corresponding to ratios of material and geometric parameters. And C22 here is just the speed in the core layer. Yeah. So let us assume that again mu is a small parameter, that rho is of the same order with mu, and the ratios of thicknesses are of order 1. So in this case, we can start with investigating cutoff frequencies. And we will see that for the cutoff frequency, well, the equation is certainly much less pleasant compared to the one that we had for the symmetric case previously, but it's still doable, because if we are interested in the global low frequency motion, that means the arguments of tans are basically small, so you can get rid of tans, replace them with the arguments, and find a solution. So there will be actually two solutions here. So one for omega equals 0 would be corresponding to the fundamental mode, and the other one is indeed this small cutoff frequency, which can be found as a small number here. So it is indeed small. And another thing that we could also do is that we could set omega to 0 and have a look at the static limit. And in this case, we will have something like this, the solution for, well, the equation for the wave number k now. And what we will see is that there is one obvious solution of k equals 0, matching omega equals 0 before, so that is the fundamental mode. But there is also, these are the solution. So, well, for people who know Russian language, this subscript is usually causing a bit of distress. But this is not U, this is boundary layer, right? So this is the one associated with the boundary layer type behavior. And you can see that this solution here is small. It can also be shown as small here. So really, it is a slowly decaying boundary layer. The fact that was known previously for strong inhomogeneous layered structures, but indeed we can see it here. Yeah. So this is roughly how this well, dispersion diagrams would be looking like, but here we're also continuing them into.
Sorry.
Yes.
So you have on the previous slide, you have k squared,
yes,
approximately equal. So this quantity can be negative, can be positive.
Yeah. So yes, because the k squared is negative, it means that this k is imaginary. So that means that imaginary k is associated with the decaying solution. So it would not be ikx propagating, but the one will be decaying. Yeah.
Right. Okay.
This is why it is a boundary layer. So if k squared was of order 1, then we would have a fast, well, rapidly decaying boundary layer, so it would be no problem. But here we can see that the effect of high contrast actually leads to the fact that this boundary layer is decaying very slowly. Therefore, previously, people did not really like this type of problems in a way, because there was, well, it was not really possible. You would never know when this boundary layer stops in a way. It could be quite a wide distance. Yeah. Good point. Yeah. So if we want to consider the dispersion diagram, so this is the fundamental mode, this is the second mode, and it starts from this cutoff frequency here. But we are also showing here, so this part here is real value of k, this is a continuation, this is imaginary. So clearly, if omega becomes less than this value here, the solution for k becomes imaginary. So you can still see it here. And then it reaches this point here where you have a k equal to, when omega is equal to 0, and there is a solution for k. Well, this is the case of no contrast. So obviously our approximation for this value of k boundary layer or the cutoff frequency are not expected to work, and they are not working indeed. However, if we look at the case of high contrast, then indeed both of these values are on their place. Okay, so I think I will be finishing shortly so that I don't interfere much with your lunch. Just to show a bit more, so we can also derive the shortened dispersion relation, the approximation of it, and it shows already a two-mode structure. So there is a product of two quantities here. So the first bracket is corresponding to the fundamental mode here, and the second one is corresponding to this next low-frequency mode. And remarkably, it also covers this this part of the graph when k is imaginary. So the one that is corresponding with decaying solutions already, so decaying modes. And so you can see from the equation here is that, well, actually, if you want to say make omega smaller than this value here, then the solutions for k squared will start to become negative from a certain moment, and eventually they will end up here when omega will be 0. So I think I should be stopping here for today, and tomorrow we continue. Yeah. Thank you very much, Kirill.
Thank you.